Moving along, the next we're going to talk about is 30. 30 says the following. Which of the following compound precipitates from a solution that it has concentrations indicated? CJ for the KSP values. So they say that they have KClO4 with the K concentration and the ClO4 concentration. So you have KClO4, and you have the K concentration, or the K and the ClO4, and you know that the KSP for this is going to equal the concentration of K times the concentration of ClO4. Now if you multiply the values they have here, you get 0.1 times 0.1, or 1 times 10 to the minus 4. Now you just look up in your solubility products table to see what the solubility product for KClO4 for potassium chromate is, and it's 1.05 times 10 to the minus 2. So it's 1.05 times 10 to the minus 2. Now what that tells you, since this number that you calculated is less than this number, it means that it will not precipitate. If this number is greater than this number, then it does precipitate. And I bet you money this next one is probably an example of that. We have this potassium platinum chloride, which goes to form 2 potassiums plus the platinum chloride. So the KSP here is equal to the potassium concentration times squared times the platinum chloride concentration. And the numbers we get, the potassium concentration is 0.01 again. But this is squared now, and is also 0.01. So basically it's 0.01 cubed, which is now 1 times 10 to the minus 6. We look in the table again, and we see that the KSP from the table is 7.848 times 10 to the minus 6. Now again, this number, even though it's just a little, it's a little less than this number. Therefore, it will not precipitate. I'm going to do the third one, which is potassium iodide. Again, this goes to lead iodine, This goes to lead plus 2 iodine ions. The KSP here is going to be lead 2 plus times iodide squared. And the concentrations they give you this time are 0.003 and 1.3 times 10 to the minus 3. We do the math here, and you get 5.07. This is minus 6 minus 3 more times 10 to the minus 9. And we look up in the table now, lead iodide. We see that's 1.4 times 10 to the minus 8. Again, this number is less than this number, so it will not. The last one, silver sulfide. goes to form silver, 2 silvers, plus sulfide. KSP here is silver ion concentration squared times sulfide. And the concentrations now are 1 times 10 to the minus 10 and 1 times 10 to the minus 13. If you square this, it's 1 times 10 to the minus 20. Multiplied by that, it's 1 times 10 to the minus 33. If we look up silver sulfide, it's 1.6 times 10 to the minus 49. Now, this is greater than this, so it will precipitate out. So this last one is the only one of the ones that we were given in this problem that will precipitate out. We go to the last day. Number 33 is an odd one, which means that you can look up the answers in the back, which means I'll do 1. Actually, I don't need to do 1. Calculate the concentration of the sulfide ion that just begins to precipitate a solution that's this molar. So you look up the KSP in the back. You put in the concentration of barium, and then X is the concentration for sulfate, and see what X comes out to. So that's number 33. Number 36, calculate the concentration of F required to precipitate calcium fluoride in a solution that's 0.01 molar calcium. Well, let's do that one. This is very similar to the 33, which you're going to do on your own and look up the answer. So you have calcium fluoride. That goes to form calcium ions plus 2 fluoride ions. So the KSP here is calcium 2 plus and fluoride minus squared. And what they're telling you here is that the concentration here is 0.01, and they want to know what concentration here will lead to initial precipitation. Well, in order to do that, you have to look up the KSP value for calcium fluoride, which is 4 times 10 to the minus 11 times 10 to the minus 11. So it's going to equal 0.01 times X squared, because this is squared if this is X. And so if you do this divide both sides by 0.01, you get 4 times 10 to the minus 9 is equal to X squared. So X is going to equal to the square root of 4 times 10 to the minus 9. 6.32 times 10 to the minus 5. So the maximum concentration of fluoride that you can add before this precipitates is this concentration. Now the last two problems are both odd, which means that their answers are in the back of the book. But again, I'll do 1 in order to, and I think some of you all asked me a question about this earlier, like a couple of weeks ago. But the way, let's take 45. What reagent might be used to separate ions of each of the following mixtures, which 0.1 molar with respect to each ion? In some cases, it may be necessary to control pH. Consider the KSP value. Okay, so if you have copper and mercury, okay, what you have to do is go to the table in the black and look at various copper possibilities. And you can see that, for example, copper sulfate is very insoluble, 2.5 times 10 to the minus 48. And copper chloride, on the other hand, is probably the most soluble at 1.2. So pick the least and the most. So copper, so this is 45A. So copper, you have copper chloride, which is 1.2 times 10 to the minus 6. And then really bad, or really insoluble, is copper. I'm sorry, this isn't a 2, it's just that. Let me make sure on the problem we're dealing, oh, it's 2 plus, excuse me. Let me do that again. Because I picked out copper plus. Well, it doesn't have one for, copper 2 plus. You have to pick one that's 2 plus. So let me erase that. Because you can't pick something that's plus, you have to pick something that's 2 plus. So copper carbonate is 2.5 times 10 to the minus 10. That's copper carbonate. And copper sulfate is 8.5 times 10 to the minus 45. So that one's pretty bad. And copper hydroxide is kind of in between, so let's not write that one down. And the rest of these are mono. Now let's go to mercury, and that's in those you can see we'll have Hg2, okay? So Hg2 is what you're looking for. And what you can see, you have Hg2O, Hg2Cl, but you need to pick one of these two because this is what you have. So let's see. We have Hg2 carbonate, okay? So Hg2 carbonate is 9 times 10 to the minus 15. And the other one would be Hg2S is 1 times 10 to the minus 47. So these two aren't very helpful. But this, if you added carbonate, you would precipitate out Hg2CO3 first before you precipitated out this one. And so carbonate is one that you could use to separate these two. And that's how you do these problems. You pick. And I think when I answered it the last time, I answered it incorrectly because I failed to see that it had to be copper 2 plus, and I apologize for that. But for example, if you wanted to separate, now sulfate versus chloride, that's more complicated because the table is listed by cations instead of anions, so you're going to have to look through the table more carefully. And there are probably several possibilities in there to use. The last one is number 47. It says the solution contains 1 times 10 to the minus 2 molar Ki and 0.1 mole of KCl per liter, which is 0.1 molar. AgNO3 is gradually added to the solution. Which forms first, solid AgI or solid AgCl? All you have to do again is look in the table and see which one has the lowest solubility constant, and that's the one that'll form first.